Is everyone ready? Let's get ready for chemistry!
There are actually two types of bonds. There are sigma bonds and there are pi bonds. The sigma bond is a direct overlap between two orbitals. The pi bond is an indirect overlap between two orbitals. So the sigma bond is the first bond, and then the pi bonds are the double and triple bond. Let me show you. Chlorine, according to Lewis theory, will bond with chlorine to make a single bond. The chlorine atom has p orbitals coming out at all angles. The other chlorine atom also has p orbitals coming out at all angles. And when these p orbitals get close enough to overlap, they create the sigma bond. So the two chlorine atoms have p orbitals in their valence shell that overlap, creating a sigma bond. It's a direct overlap of two orbitals. When hydrogen bonds to hydrogen, the s orbitals overlap, and that creates the sigma bond. So when their two orbitals overlap, they create a sigma bond. In the methane molecule, the carbon in the second energy level has s and 3p orbitals. Now, these orbitals do not all have the same energy. So if the carbon is going to need 4 equal energy orbitals to place the pairs of electrons in the bond in, then it's going to need 4 equal energy orbitals, and it doesn't have those. The s orbital and the p orbitals don't have the same energy. The carbon must therefore hybridize its orbitals so it can have 4 equal energy orbitals. So it's going to average out the energies of the 4 orbitals. The s orbital is going to have to gain energy, and the p orbitals are all going to have to come down in energy a little bit. And so these 4 orbitals are going to be an average of 1s and 3p. So they're going to be sp3 hybrid orbitals, because in order to make them, we had to average an s and 3p's. Now the carbon had 4 valence electrons. In order to create 4 equal energy bonds with the 4 hydrogens, the carbon needs to remove an electron from the s orbital and promote it to the p orbital so that it can have 4 equal energy electrons in the sp3 orbitals. So it can have 4 equal energy electrons to get ready to bond to the 4 hydrogen atoms. So the carbon averages its orbitals that when hydrogen comes into bond, it can form 4 equal energy bonds with the hydrogen. Boron is located in the second energy level. It has s and p orbitals. Boron has 3 valence electrons, filling up from the lowest energy. But in order to make 3 equal energy bonds, it needs 3 equal energy electrons. Therefore, it needs to create 3 hybrid orbitals so that the electrons can all have the same energy so that we can create 3 equal energy bonds with the 3 hydrogens. So to hybridize these orbitals, the s is going to come up quite a bit and the 2 p's are going to come down a little bit in terms of energy. That's going to make 3 equal energy hybrid orbitals and 1 p orbital that was never touched. So we're going to hybridize the first 3 orbitals. That's going to make an sp2 hybrid orbital, an orbital that's an average of 1s and 2p's. So we're going to have 3 equal energy sp2 orbitals, and then we'll have 3 degenerate orbitals for our 3 electrons. And then when the hydrogen comes into bond, the hydrogen can have a place for that electron to come share that's all equal in energy. So the hybridization in the BH3 molecule is sp2 hybridized. Only the sigma bonds require hybridization. The pi bonds are going to be placed in unhybridized p orbitals. So when we're counting the hybridization, we're only counting the number of sigma bonds. If we had 2 sigma bonds on the central atom, we would need the first 2 orbitals. We would hybridize them and make 2 equal energy sp hybrid orbitals. If we had 3 sigma bonds on the central atom, we would need the first 3 orbitals to hybridize. We would average their energies and make 3 sp2 hybrid orbitals. If we needed to have 4 sigma bonds, we would need the first 4 orbitals. We would average these 4 orbitals in terms of energy and make 4 equal energy sp3 hybrid orbitals. Now there's some debate about 5 and 6. But remember that you've got some d electrons in here as long as you're in the 3rd energy level for your valence shell or greater. So if you look at the first 5 orbitals, the hybridization here would be sp3d. And for the first 6, you would need sp3d2 to have the first 6 hybrid orbitals. So if you want to know the hybridization of the central atom, look at the number of sigma bonds that the central atom is making with the outside atoms. Remember that a sigma bond is the first bond that's made in every case, and the double bond is not a sigma bond. So the nitrogen in the nitrate ion, and it's got resonance structures, no one cares, begins with its valence electrons in the 2nd energy level with 5 valence electrons. Now, as it gets ready to bond, it's going to require orbitals for 3 equal energy sigma bonds. So it's going to have to hybridize the first 3 orbitals and create 3 equal energy sp2 hybridized orbitals and then 1 p orbital. So the sp2 hybrid orbitals will have 1 electron in each, and then a couple more p electrons unhybridized. When it comes time to share the electrons with the oxygens, there will be a direct overlap between the orbitals between the oxygen and the nitrogen in these hybrid orbitals. So the nitrogen will make a hybrid sp2 orbital that the oxygen will then come in and create a sigma bond with. And it's going to do that 3 times so that it can make 3 sigma bonds with the 3 oxygens. And yeah, what you get here is the disaster, as the picture goes, but we're making 3 sigma bonds. After you make your 3 sigma bonds, we don't have an octet yet, so we're going to make a pi bond. A pi bond is an indirect overlap between 2 unhybridized p orbitals. The bond between the nitrogen and the oxygen is a sigma bond. It's that direct overlap between the 2 orbitals. P, S, hybrid, whatever, it's a direct overlap. And then nitrogen and oxygen both have some p orbitals sticking up. So if they overlap outside of the plane of the atom's nuclei, then what they're going to create is a pi bond, an indirect overlap between the 2 atoms. And that indirect overlap comes about because of the peanut-shaped p orbitals that the nitrogen and the oxygen have. We need resonance structures because the double bond is not actually on any one oxygen. The first bond is always a direct overlap between the two nuclei, and then you've got these p orbitals outside of the plane of the atoms sticking up and down. Now you're going to have to imagine this being flat. What can happen here is that the extra pair of electrons making the pi bond is actually occupying all of these, overlapping all at the same time. So there's an overlap here of these p orbitals. They're all overlapping and creating that pi bond that's being equally shared between the nitrogen and all three oxygens at the same time. So it ends up being about a bond and a third of a bond because that extra pair of electrons is being shared around all three of those positions simultaneously. Lewis' theory predicts that the nitrogen would have a triple bond in between them. What sort of bonds are in this molecule? The first bond in the nitrogen molecule is the direct overlap between them, the sigma bond. The second bond in the nitrogen is an indirect overlap of p orbitals, a pi bond. And remember that there are 3 p orbitals. So there's also a p orbital in front and behind an indirect overlap of electrons, which is also a pi bond. So the nitrogen molecule does not have a single bond, a double bond, and a triple bond. The nitrogen in the nitrogen molecule has 1 sigma bond and 2 pi bonds. Each bond after the sigma bond is a pi bond. So how many sigma bonds are there in formaldehyde? The first bond is a sigma bond, so there's 3 sigma bonds. And then for every double bond you have a pi bond. So in this molecule, there's 3 sigma bonds and 1 pi bond. What about in the acetate ion? The acetate ion has 6 sigma bonds and 1 double bond, 1 pi bond. The hybridization of the carbon here is sp3 because it has 4 sigma bonds, and the hybridization of the carbon here is sp2 because it only has 3 sigma bonds. The pi bond doesn't count towards the hybridization. Benzene has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sigma bonds. And then each bond that's not a sigma bond is a pi bond. So 1, 2, 3 pi bonds. The hybridization of the carbon here with 3 sigma bonds is sp2 hybridized. Styrene has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 sigma bonds, and 1, 2, 3, 4 pi bonds. The hybridization of this carbon here with 3 sigma bonds is sp2 hybridized. Here we have 2 sigma bonds and then 2 pi bonds. And since the carbon has 2 sigma bonds around it, the hybridization of the carbon here would be sp hybridized.
Is everyone ready? Let's get ready for chemistry! Ah!